Section 4.4, Day 1, the fundamental theorem of calculus. Okay, so far we've looked at the antiderivative of an indefinite integral. And we know that we call it indefinite because there's no boundaries. And the antiderivative, we represented that with big F of x plus c. And we called this the general antiderivative. Okay, then at the end of lesson 4.3, we said, okay, well, what if we put boundaries on an integral? So if I look at 1 to 4, negative 3 dx, then what does this mean? And we said this was the area, used loosely, of the region bounded by the function y is equal to negative 3, the x-axis, and the vertical lines x is equal to 1 and x is equal to 4. So on the xy plane, we were able to sketch these functions. So we'll put this as y is equal to negative 3. Between x is equal to 1 and x is equal to 4. And I put area in quotations because we know area has to be non-negative, but because the region lies below the x-axis, it has a negative value. So length is 3 units, width is 3 units. So it's the opposite of the area of a rectangle, which is length times width. So this evaluated to negative 9. Now it's unrealistic to think that every single time we evaluate a definite integral, we're going to be able to sketch the functions and use exact geometric formulas to find the area of those regions. So the fundamental theorem of calculus. Alright, so this is a biggie. To evaluate a definite integral, okay, definite integral because there's boundaries, we find the antiderivative. So think of our rules for antiderivative. We have our power rule and trig rules only. We find the antiderivative, plug in the upper boundary, and subtract the value you get when you plug in the lower boundary into the antiderivative. Now, definite integrals will always evaluate to some given number, okay, and that number can be positive, negative, or 0, but whenever we use the fundamental theorem of calculus, our answer is going to be one single value. Okay, so let's look at the one we just did. We already know what this answer should be. So according to the fundamental theorem of calculus, we find the antiderivative. So the antiderivative of negative 3 would be negative 3x plus c. And for notation, and we'll practice this, I plug in the upper bound, which is 4. Subtract the answer I get when I plug in the lower bound, which is 1. Okay, so again, according to the theorem, I plug in the upper bound into the antiderivative, and I subtract the answer I get when I plug in the lower bound. So this gives me negative 12 plus c, and that would be plus 3 minus c. And notice that these c's cancel each other out, and it verifies that we get an answer of negative 9. Because a definite integral will always evaluate to a number, when you find the antiderivative on this step, you never need to include the plus c. Now this is different than when we solved differential equations and we had something like dy equals negative 3 dx. And when we found the antiderivative, we said each side needed that constant term. And then we lumped them all together to be the one big plus c. We were integrating two different functions here. That's why we needed two different constants. This has the exact same antiderivative of negative 3x plus c. So you'll see me use it as we apply the fundamental theorem. You'll never include the plus c. Okay, they'll always cancel each other out. And it helps with notation. We don't get lost in remembering to include all of that information. Okay, so use the fundamental theorem of fundamental theorem of calculus to evaluate each. And just remember, if we're going to find an antiderivative, we know f of x must be continuous on the closed interval from a to b. So just a quick spot check of the domain, and we'll be able to proceed. Alright, the antiderivative of 5x between 0 and 2. Okay, so the antiderivative using the power rule, 5x squared over 2 between 0 and 2. Fundamental theorem says plug in my upper boundary, subtract the answer I get when I plug in my lower boundary. So this would just give me an answer of 10. Now again, the plus c, I said when you took your first quiz, don't forget the plus c. Now you don't need the c at all, and you'll see that you'll lose that quickly. Another thing we can do here, remember that 5/2 is just a coefficient, so we could just plug in the 0 and the 2 into the function x squared. You get the same answer, but when we have more than one term that we're integrating, this sometimes becomes a useful tool. From 2 to 5, negative 3v plus 4 dv. So the antiderivative, add 1 to the exponent, divide by the nu, plus 4v. Okay, so negative 3/2, 5 squared, plus 4 times 5. So that's all of the antiderivative, 5 plugged into the antiderivative, minus negative 3/2, 2 squared, plus 4 times 2. Unless otherwise stated, these are all non-calculator problems. Okay, so plus 20 plus 6 minus 8 plus 18 so negative 39/2 would be the value of our antiderivative. This is the hardest part. The substitution is easy, and then the number manipulation. Okay, so the integral from negative 2 to negative 1, u minus 1 over u squared du. Okay, domain of this function would be that u can't equal 0. That's not in the interval, so we can use the fundamental theorem. So let's rewrite this as the power rule. This would be u to the negative second power. Add 1 to the exponent, divide by the nu. Add 1 to the exponent, divide by the nu. Plugging in negative 1, 1/2, minus 1. Plugging in negative 2, 4/2, minus 1/2. Okay, barring any mistakes. Find my mistakes for me. Negative 2 would be our answer. So again, answer can be positive, negative, or 0. Integral from 0 to 2, 2 minus t times the square root of t dt. So we have to, the domain would be t is greater than or equal to 0. So we can proceed. It's continuous on the closed interval. We just have to rewrite it using the power rule. So distributing this in, t to the first times t to the half would be t to the 3 halves. Add 1, dividing by 3 halves would be multiplying by 2 thirds. Add 1, dividing by 5 halves would be multiplying by 2 fifths. So we have 4 thirds t to the 3 halves minus 2 fifths t to the 5 halves from 0 to 2. We like seeing a boundary of 0. Minus 2 fifths 2 to the 5 halves. So that's at big F of 2 minus 0 when we plug 0 in. And you're going to hate this answer, but this is it. So 2 cubed is 8, and the square root of 8 minus 2 fifths. This is 32, so square root of 32. Alright, 4 times 2. 8 thirds root 2 minus, this would be 16 times 2, so minus 8 fifths root 2. And what would this give us? 40 minus 24, 15 root 2. Okay, power over root. We lost that a little bit on the quiz, so that would be your final answer. Integral from 1 to 8, square root of 2 over x dx. Domain, x has to be bigger than 0, continuous on the domain. So let's do a whole lot of rewriting here. This is square root of 2 all over square root of x. I'm going to bring that square root of 2 out front. Rewrite the integral as x to the negative 1/2 power. Applying the power rule. Add 1, dividing by a half is multiplying by 2. So we have 2 root 2 as a constant. And then I just need to apply the fundamental theorem to the x. So 2 root 2, we have square root of 8 minus 1. So 2 root 2 minus 1. This would give us 8 minus 2 root 2 as an answer. Trig, 0 to pi, 2 plus cosine x dx. Antiderivative of 2 would be 2x. Antiderivative of cosine would be positive sine of x between 0 and pi. So plugging in pi, we get 2 pi plus the sine of pi. Minus plugging in 0, we get 0 plus the sine of 0. Don't look at a boundary of 0 and just assume that it completely eliminates the function. So we have 2 pi plus 0. This one, it does. Our final answer would be 2 pi. Alright, so homework for our next class, the first time we see each other. Page 293. Alright, using the fundamental theorem, numbers 5 through 21 odd, 22, 23, and 27 to 34. These are your trig problems, so let's focus on them. Do all of those. All right, enjoy the rest of your break.